So our speaker for today is Benedetta Piroddi, and she will talk to us about Moduli space of framed elliptic curves. Please, Benedetta.
Thank you, Fede, and thank you to all of you. And yeah, first of all, I want to cite my sources. So my source, singular here, is the thing you can find on the archive. The author is Ain, and it's called Lectures on Moduli space, species of elliptic curves. And basically, this is the first like 15 pages or so of his lectures, and they are very clear. And if you want to like, I want to like, for instance, I want to do any proof. The proofs are in there if you want to look at them, and if you want to, I don't know more about this topic, you can find everything on the archive. You just search it out on. Okay, so. Okay, first of all, I want to recap some things that already Martina told you last time, just to like fix notations and ideas and everything. So for us, an elliptic curve, basically we have two points of view we can take to study them. So the first is as compact Riemann surfaces of genus 1, where you choose the point, which will be your 0 point, basically. And so basically pointed curves. On the other hand, you can look at them as functions of the complex space by a lattice. So L is something like Z1 plus Z2, where L1 and L2 are linearly independent over R. Okay, so we want to like say something more. Like this is the heart of what we are looking at, and we want to give more information of how to like go from one side to the other. So that's what the moduli space construct is about. Okay. So, okay. So first of all, if you start here, okay. Okay, so C is our Riemann surface. So you start here. This surface has genus 1. This means, by definition, that this space here is generated by a holomorphic form. So from now on, we will fix this omega as a generator. Now we take on this side. On this side, I take lambda, which is the set of integrals. So the integrals over gamma, for form omega, it's the same omega as there, such that gamma is in the H1 here. So, okay, so this is basically the set of paths how to you know how the space is defined. And so here, and this is a lattice because if you take so this is over Z, so this has dimension 2, and we take a basis of it. Let's call it sigma 1 and sigma 2. Then we call lambda j which is the integral over sigma j of omega. And these are these two values. Okay. So you pass from the Riemann surface structure to the complex torus structure via this. Okay. So a consequence of this is that, so on this side, we have a group structure, which gives us that actually we have a correspondence between basically homomorphisms of groups on this side and the holomorphic functions on this side. So let me be a little bit more clear. So our elliptic curve, C, this side here, has actually a group structure. Which is basically given by this correspondence here. And P is the identity. And the multiplication and the inverse map are actually holomorphic. So the iteration of the group basically is holomorphic. And what this, if you look at this on this side, then what we get is that a function f from c over lambda 1 to c over lambda 2, which is holomorphic, this implies that there exists a complex number such that lambda 2 is c lambda 1 is contained in c lambda 1. So maybe the other way around, yeah, the other way around, okay. Okay, and f of z plus lambda 1 is c z plus lambda 2. And we have isomorphisms when we have an quality here. Okay. Isomorphism, this is an equal, and of course C is invertible. If this is equal, and C is invertible. Okay. So now that we have this picture, let's talk about what is the moduli space. So basically, a moduli space is a kind of geometric object that parameterizes the objects we are looking at, in the sense that we want to have a space X, of which each point represents an elliptic curve. Something up to isomorphism. And we want to have something more, of course, because the thing is that this has to be a geometric object, not only a set. And basically what we want to say is that if we deform slightly the curve C, and I will talk a little bit more about what this means. Basically, if you deform slightly C, then you move in this space very little, very near. And we want to, of course, to do this in a mathematically appropriate way, because this is all talking. So basically we want we want X to have a structure which is compatible with this deformation in the curves. So deforming C to a C prime, which is near to it, we move very slightly, and we want everything to be holomorphic. So if we have holomorphic maps on the bottom, we also have everything holomorphic, and all the diagrams that we will be looking at also have to be made up of functions. So let's do it like properly in a mathematical way. So the thing is that it's a lot easier to work with framed elliptic curves, which is why that's in parentheses. So what is a framing and why do we need it? Basically, to choose a frame means to choose this basis as an ordered basis. So as sigma 1, sigma 2 will be different than sigma 2, sigma 1. And also we want to choose them so that they intersect in one. So basically they intersect in only one point. If you think about it if you want an image of it, you want to choose sigma 1 and sigma 2, which are something like this. So they intersect in a point, and what else? Oh yeah, and then they are ordered, so we cannot swap them. Let me write it down maybe. So we just to fix the limitations and everything. So framing of our currency is a choice x, y of that is derivative of h1 of 0 z, and then such that the xy is 1, so intersecting 1 point, and then this is ordered. So maybe I shouldn't write it like this, but like this, just to be used like coherent notation. So this is different than the other one. And of course, if we switch to this point of view, what we get is a lattice, a framed lattice, which is a lattice lambda, lambda 1, 2. So a lattice with the choice. And this is exactly as you imagine. So lambda 1, lambda j, lambda 1 will be the integral over x of our form omega, and the lambda 2 will be the integral over y. Okay. And since here we have this condition, what we get is that actually lambda 2 over lambda 1 always belongs to the half upper plane of the complex space. So here. And because of this whole code here, actually we always get from like starting from any lattice here, we can always choose basically a normal form of this lattice, which is like this. So we can our lambda is always isomorphic to a lattice of this form here, where tau is our lambda 2 over lambda 1 and belongs to our h. So we're getting somewhere. We are getting that each point of the half upper space in some sense represents a lattice. And then we have that each lattice represents curve. So this is like pretty close to the object we are trying to describe. Let's like fix some videos about this. So as I said, we have our space H, and this corresponds to the isomorphism classes of framed lattices. And this corresponds to the isomorphism classes of framed elliptic. With the correspondence that goes here you have tau, here you have your lattice lambda like z plus tau, and here you have your tau is actually for any lambda 2 and lambda 1, such that you have this. On this side you have the curve C, which is C over this lambda. We always have this side. Just one small. Okay. So as a set, our modular space of framed elliptic curves is H. But we will see that we can put more structure on H to take into account that I'll talk about the deformations, which will be I will be explaining it better in a few moments. So our H as a set is the modular space of framed elliptic curves. And if we want to get from this to the modular space of elliptic curves, we have in some sense to forget about the framing. And there is a proper way to do this. So it's a basis of the first homology group, yes, of integer coefficients. So it's a basis which is ordered and which give intersection one, the two elements of intersection one.
So you're connecting the homology with the homology.
Yep. Yep.
So that the intersection is like a single form.
Yeah, I mean you can define the intersection form such that basically it's the number of intersection points, but you have also a minus, like they can intersect in a negative number, and they can also like you can add some.
So for you, it's like a wedge.
Yeah.
Like
Yeah. Yes. Yes. Exactly.
And you can always have a framing on any.
Yeah, we will get to it. Yes, but basically yes, because you are only choosing a basis with some properties.
Because in that last correspondence, like at least in the basic theories I've studied, like you always define C. One of the definition of elliptic curve is that. So that made me to ask, like, you can always have it.
Yeah. Because it's a modular space. So yeah, we will. I mean, I will say something more. I mean, this concept of a framing, basically, like you are asking very little. It's just to make the structure easier in some sense. So yeah, you can, because the thing is that if you then want to get more structure over this H, so you want to get it as a proper modular space, fine modular space, then like the whole deformation stuff, you can do it very well on H, but now we will define like the set that corresponds to the modular space of elliptic curves without a framing. But then to get more structure on that, actually you have to introduce a lot of more stuff, a lot more theory, And of course, I won't do that right now. Yeah, basically, it's a lot easier. Everything is easier if you consider it as
It's not just the thread, but even.
Hmm?
So this edge is not just a thread, but you can also put more.
Yeah, exactly. I will do it in 2 minutes. Like first, I want to describe how you get from this space, so from the modular space of framed elliptic curves to the modular space of elliptic curves without doing. So how you do this? So now we are talking about and okay, so now basically it amounts to how do you change from a framing to another one over the same curve. So you start from your very basis, but let's put it like this for, I think that it's only for, you can switch it. In the like the kilowatt, so keep it like this. You switch from a frame to another by using a linear transformation. This is basically because here we are working with this type of objects, so Z modules. So we're using the matrices. We're doing linear algebra, and this we don't want to choose any matrix here because we have to preserve this intersection, which means that our ABCD, let's call it gamma, belongs to the special linear. Because since we have that x, y is 1 and also x prime, y prime is 1, this means that this matrix has to have determinant 1 and so has to belong to SL2. And this basically describes every change of framing, which means that the space we want to look at is actually Z, H over SL2Z. But we can do it better in the sense that here we described an action of SL2Z on the frames. So we are looking at the left side of the blackboard that was before and then out. Now we want to transfer this to an action H, but this is quite easy because remember that here we started, we had the correspondence here between our tau and here we have our lattice, like this, so triangle lattice. And then here we are acting, sending, this is our basis. So we are sending lambda 1 tau to lambda, C tau SP, and A tau plus E, which means that here in H, we are looking at this is multiplied by gamma. Here, multiplied by gamma gives you CT plus D over E. So this is the action we want to look at. Yep, so it's PT plus P. This is why, yeah. So I wanted to do it as in the notes, but then, of course, I had in mind the other way around, which is the way you around it. This is what happens when you try to follow the stuff and then remember other stuff. Okay, so this, as I said, is the complex space. But we can do also a little bit better, because actually, but I don't want to do this. Yeah. We can put on this object a Riemann surface structure. So this it's actually a Riemann surface. Which we will call M11. And the nice thing is that there exists a unique way to put a Riemann surface structure over this, such that the quotient method, so from H to H over SL to Z, is holomorphic. So there is only one way to do this, and so we will choose this structure here. Which is I don't know, really nice, because our object is not only it has more structure over it, but yeah, the thing is that now we will go back to frame the stuff in a second, because actually this does not behave well under the conditions. Okay, so what do we want from a modular space? Let me like input this and write everything else. Okay, so let's take T, which is a complex manifold. We define a holomorphic family of elliptic curves over T as X, which is another complex case, another complex manifold. Then we have a net, which has to be holomorphic. And then we also want to have a section. So put that here, we have I and we have X. And we want something more, which is that if we take here 2 points on T, here we take the image of our space. So this is S from T. We want that each fiber is an elliptic curve. And the 0, so the special point of our elliptic curve, is S of T. small t. So our special point P is actually this. So this is S of prime, and this is S. So we have this, and this gives us a map that we will call P, that goes from from T to M1, S, so M1, so to this right here, which through every small t associates the elliptic curve described by this, so X t and S as a special point. And this is called the period map. And we want to ask things about this map. So, if if it were a proper modular space, a modular space which has all the stuff that you want from it, this is the stuff that you want from it. But we will see that actually we don't have it. But we would like that first thing is that it is homomorphic. Then we want that if we have a map from a space, so P is any complex manifold, and T to M11 is a holomorphic map. Then we want this to be actually a family like this. This should be family of elliptic curves over T. And then the third thing we ask is that there exists a universal family which means well, what you expect from the universal properties of stuff. So you have these diagrams. Number one. Here you have any map P, and this. So here you have some P X. Here we have any holomorphic family. Here we have our universal family. Here we have P, and we want this to actually be isomorphic to the fullback. We call this Px, and we want Px to be unique to isomorphisms of this family, or the family absolutely, that are the identity of the section. That's basically. So the family is defined by having a T, X, I, and S, and we want that on S, this isomorphism of family is the identity. Such that for every X. Okay, so we want to have a universal family, which means that for every other family, we have a factorization like this through the pullback. Okay, let me go on this side now. And the thing is that we will see at the end, I will just say one thing about why this doesn't happen on M1, but we can make it happen on H. So we go back to range first, and so that I can construct it. Okay, so the first thing we want to do actually is to define the universal family. So we call it the universal elliptic curve, which is EH over H. So it has to be like this, but here we are putting the H instead of M1. Okay, so this is our base now. And we want to construct our space. So we want some complex manifold with a projection such that the fiber over any point of H is an elliptic curve. And how do we do that? Well, let's take to start. Let's take secant H, and we take as projection the projection. The second, the projection of over the second vector, basically. Now, the fiber over any point now is. So what we now want to do is to take some quotient over of secant H, such that this fiber is not C, but an elliptic curve. We want it to be C over lambda tau, actually. So, this is so how do we get here? We define an action of z squared on sinus H, which goes like this. So we take a pair of integers, and we send each point of this space that I will write in coordinates. We will send this to, let me get it straight. Z1 plus n tau, Z2 plus n. And then as the identity on the set. Okay, so now what we are actually doing on C by this action is that we are translating by lattice points for the lattice L tau. So on C, translation by lattice points of lambda tau. So what we actually do is take this quotient, so C times H, take the quotient for the action of z squared, given like this. Then now we call this H. And this. now pi minus 1 of tau, actually c over lambda tau as we wanted. Okay.
Just clarifying, C1, C2 are the coefficient are like writing on every point in C seen as R tensor lambda 2, right?
Sorry?
C1 and C2
Yes.
are an element of C.
Yes,
Okay,
as
so
r squared.
okay, but the R square base, the base is given by lambda 2 or this is what? Mix.
Well, actually, it doesn't matter because okay, so you have your C. What you want to do is to find our lambda tau, basically, and we have our tau. So Z1, Z2 is actually any point of C in the standard basis. When you add to it an element of this lattice, as this is, so you are translating by points of the lattice. So for instance, if our lattice is something like this, I don't know, and you're sending, I don't know, this point to, yeah. And so you are actually taking the quotient over the points of the lattice, and you're getting an elliptic curve.
What is M2 then?
M,
Because now M2 is not a real number functions. That basis.
it shouldn't be. No, wait.
The writing does not make sense if you choose a standard basis. C1 is that's M2, just means C1 plus M because the vector basis is tau. Very cool.
No, no. Tau is wait. No, you're right. Yes, yeah. That's true. Sorry. Thank you. Yes, of course, because otherwise you are summing a coordinate to another complex number, and so it doesn't make sense. Yes, you're right.
Why don't you already take C mod lambda?
Oh, you want each point of your basis to correspond to a different elliptic curve, so you cannot take C over lambda here, because then varying this point you have to vary the lattice.
So then you get a single elliptic curve for each.
Yeah, exactly. A different curve for each one.
Which is like
I mean,
it doesn't make sense.
no, I mean, it is okay. This way you get like for each point, you get the elliptic curve. The fiber is the elliptic curve defined by that point in that way. Like in a way we discussed. If you try to do it the other way, like you like essentially try to like for each like take the space given by like elliptic curve, each elliptic curve, and then glue it to say that you can glue it together in some odd mystical manner.
Like the vector one.
Yeah, but that's way more complicated than just say one by this action.
Like this, you're constructing it exactly to be what you were looking for. It's not like you take a bunch of fibers and then you try to define a structure on it. Okay.
But they should be same.
Yes, no, they are the same. The problem is like the second, this way makes sense. The other way, I don't know, like how to prove the complex structure. There exists a complex structure.
Exactly, because you want to like try and imagine what the object should be, and if you have just a bunch of fibers, the global object could be anything for what you can guess. Like this, you're just building it exactly to be what you're looking for. So it makes more sense. So I have to wipe out, I think. Okay, so this is okay, almost correct. So actually, what Simone said more correct. So actually, let me fix this. Z1, Z2, Okay, so let's call this Z. And let's send it to
I think it's just fine if like Z1 and Z2 is the writing in as
yes.
R plus
Yes.
R plus R.
Set out this. Yeah, thank you. Okay, now we want to like get back to framings. So yeah, want to define a framing in such a way that it's defined over the whole base. Otherwise, again, we run basically the same problem that we're explaining now. So basically, you want also the framings to be compatible with the deformations. Okay. So we take again IS the family, and we take the point on the base, and we suppose there exists an open ball such that XU, which is just to the minus 1 of U, is actually isomorphic to U times X0 as a smooth manifold. So we want to be able to trivialize basically in neighborhoods of points. Like suppose we want to suppose that we can, take balls that are small enough to be able to do this basically, and that it's actually possible. We have to put that as an hypothesis. Okay, so now this is an open ball, so it's contactable. And so we have maps induced in homotopy. Because, basically because we have the inclusions, which are, since this is contactable, these are homotopy invariants, homotopy equivalencies. Okay, sorry, my apology. Okay, so these are equivalencies, which gives for this J, which gives for any pair S and P, you actually get isomorphisms, each one on the fibers on the origin. Each one of us. Each one of S. This is the but it's I think it's the JT upper star over the woods. To write down things.
Do you take, sorry Benedetta, you take the point in T or in U? In open ball? Okay, and I have another, I have another question. When you say it's compatible, maybe you said before, but I not catch everything what you said. What do you mean when you say, okay, it's compatible, so this inclusion is homotopy equivalent? Can you explain better? I don't get the.
Contractible. It's an open ball, so it has trivial P1 and
Okay. Okay. No. Now it's fine. Stupid question. Okay.
contractible. Okay. Is it the correct English? Do you sexually contractible?
No. Yeah. I heard another word. This is the point.
Okay, thank you.
Thanks.
Okay. Okay. So you have this thing here, and now you define. You get the definition at the end of this, which is that a family of elements of this form. So now, which are elements in each one of X, etc. So again, you are varying the T. You say that this is locally constant. If for any okay, so if for any open ball that gives you a trivialization like this, and for any pair of elements inside the open ball, the elements C of T and C of S actually get sent one into the other through this chain of isomorphisms. Basically, the theta corresponds to equal S for any pair of elements in the ball as everything that is on top via these isomorphisms. And you say that framing is locally constant if both of the parts are locally constant, and basically, and you define a framed family if it admits a framing which is locally constant. So let me write something down. So. Yeah, because I need this. Okay. Quindi you define a family is framed if it has a local constant given by x of tau, x of t, y of t. So basically, both of the parts have to satisfy the condition of being locally constant. And the result you get is that with this construction, you get that the family H of H is actually locally constant, is framed. And if T is simply connected, then any family of elliptic curves over T is framing. And then the other thing you get is that a framed family absolutely gives a period map G from E to H that sends each element on this one is on this. So it's basically the same as the lattice correspondence. And this map here is holomorphic. And moreover, X is actually isomorphic to this scalar from EH. So the conditions and this thing here is true. So this is, if you work with framed families of elliptic curves, actually this gives you all the conditions that we were asking. So everything works. But remember that we are working with H, not with M11. And what goes wrong, basically, which is the last thing I want to talk about. Sorry? Yes, I will recall it right now. It's important. Yes, because recall that we defined M1 as the quotient of H over an action of S and Z. Okay. So now we have that everything works now, or everything is working on H, but now we want to see if it also works on the quotient. And the fact is that it doesn't work well because this action here has fixed points. And this implies that actually, basically, here you have, so here, let's take H here, and our H, which is our universal family. Now, here we had the quotient one. And here we have the complement to this, the quotient here. And what we hope we can do is that any family here can be lifted to a family of H so that we can use all this machinery here. But the thing is that since the action here has fixed points, you cannot lift the identity to something to an identity of H. So this breaks down, and you cannot lift families, deformation families of elliptic curves which are not framed to an action of framed, to a family of framed elliptic curves. And the way you solve this is that you put other, like you define this quotient in a different way, so that it inherits even more structure. What you actually want to do is, I think, a GIP quotient, but I may be wrong. No. Sorry? Yes. Yes. So you can, yeah. If you want to know more about this, you should look at the notes I said at the beginning. What you want to do is you want to put an orbifold structure on this object here, and if you do that, then it becomes the proper object you are looking at. So something that satisfies these conditions, and it becomes a two modular space. Otherwise, if you can work with framed curves, if it's enough for you in your if the thing you are trying to do if you can assume that the curves are framed, then you can use this stuff, which works. Otherwise, you really have to work on this object, which is, I don't know, more complicated. So I think that's all I wanted to say.
Is there any question? Okay, if not, we thank Benedetta again. And next session is next week.
Thank you. Goodbye.